This video is about the first part of kinetics in chemistry. Rate of reaction is measured by the amount of reactants converted to products per unit of time. A variety of means exist to experimentally measure the loss of reactants or increase of products as a function of time. One important method involves the spectroscopic determination of concentration through Beer's law. The rate of a reaction is influenced by reactant concentration, temperature, surface area, and other environmental factors. As you can see in this graph, rate of reaction is calculated according to product produced over time. To generalize reaction rates with stoichiometry, we can use this equation to represent their relationships. One can gain information about the rate of a reaction by seeing how the rate changes with changes in concentration. This can be calculated by using the Beer's law, which is absorbance equals to absorptivity times path length times concentration. Reaction rate is mainly affected by the following factors: concentration, gas pressure, particle size, presence of catalase, temperature, and light. The rate law expresses the rate of a reaction as proportional to the concentration of each reactant raised to the power. There are three orders that we need to know: zero order, first order, and second order. Sum of the powers of the reactant concentration in the rate law is the overall order of the reaction. Investigation of data for initial rates enables prediction of how concentration will vary as the reaction progresses. We express this rate law as following: concentration of one reactant raised to a power, which is the reaction order of the reactant, multiplied by another reactant's concentration raised to the power of its reaction order, while the overall reaction order is simply the sum of the powers. This table sums up how we determine a reactant's order. For zero-order reactions, there will be no change at all in the rate with the change in reactant concentration. For first-order reactions, if the reactant is doubled, rate doubles. If reactant is tripled, rate triples. For second-order reactions, if the reactant is doubled, rate is multiplied by 4. If reactant is tripled, rate is multiplied by 9. We can only determine rate law from experimental data, which is presented on the test in table form. We first choose the two experiments that reactant A has no changes, then compare the changes of reactant B, which in this table, there is no change in rate even concentration of B doubles. We can say reactant B is of zero order. Please try and determine the reaction order of A on your own. This should be the resulting reaction rate of the table. We can also determine reaction order by looking at graphs. For a zero-order reaction, its graph should look like this: a negative slope with y-axis labeled as concentration of reactants. For a first-order reaction, the graph should be a negative slope with y-axis labeled as natural log of concentration of reactant. For a second-order reaction, the graph should be a positive slope with y-axis labeled as 1 over the concentration of the reactant. We can use calculus to integrate the rate law for the three different order reactions process, which gives us the following. These equations are given in the equation sheet, so don't worry to memorize them. The proportionality constant in the rate law is called the rate constant. The rate constant is an important measurable quantity that characterizes a chemical reaction. Rate constants vary over many orders of magnitude because reaction rates vary widely. The temperature dependence of reaction rate is contained in the temperature dependence of the rate constant. For first-order reactions, half-life is often used as a representation for the rate constant because they are inversely proportional, and the half-life is independent of concentration. Now, please pause the video and try this problem. This should be the solution of the problem. The order of an elementary reaction can be inferred from the numbers of molecules participating in the collision. Unimolecular reactions are first order. Reactions involving bimolecular collisions are second order, and so on. Elementary reactions involving the simultaneous collision of three particles are rare. The next part is about collision. Unimolecular reactions occur because collisions with solvent or background molecules activate the molecule in a way that can be understood in terms of partial energies. Successful collisions have both sufficient energy to overcome activation energy barriers and orientations that allow the bonds to rearrange in the required manner. We use Maxwell-Boltzmann distribution to gain an estimation of the fraction of collisions with sufficient energy to lead a reaction. This diagram shows how the presence of an enzyme helps the reaction to overcome the activation energy by lowering it.